everyone. My name is Jenna Gorlewicz. I live in Illinois in the United States, but I actually work in Missouri. You can find my work online at slu.edu/GorlewiczLab/home. But more importantly, my affiliation is with St. Louis University. I'm in the Department of Mechanical Engineering, and I direct the Chrome Lab. So if you just Google Chrome, CHROME lab, at SLU, S-L-U, you should find us. Chrome stands for Collaborative Haptics, Robotics, and Mechatronics. At SLU, I'm also Associate Dean for Research, and one of my passions is use-inspired research and translating the work we do beyond our walls. So I'm co-founder of two companies, Vital, which is an ed tech startup, and R&R, which is a vibrotactile medical device stimulation company. I'm a member of several different research communities and networks, especially those related to haptics, or the sense of touch, accessible technologies, particularly those that are multimodal, robotics, and entrepreneurship. I'm very interested in discussions related to the following questions. Number one, how do we rechannel touch as a primary mode of interaction in communication and technology design? And the second question is, what are different approaches for scaling intermodal learning systems, particularly those that have tangible components? I'm currently part of a project focused on the development of wearable haptics. So these are devices that you can wear on your body directly. So one of the images that I have shown is a sleeve-like device that extends over the hand. And this sleeve provides both tapping and vibration sensations in lots of different patterns. And one of the things that we're interested in understanding is, how do you route nonverbal communication cues and sort of core functions of communication through the haptics channel? Another project that I'm very interested in thinking about further and uncovering is something we're calling teletangibles. So I'm interested in exploring highly reconfigurable, portable, maybe even have smart, in quotes, smart capacity manipulatives as a way to interact or serve as an interaction medium to digital educational content, and to bring that hands-on, truly hands-on kinesthetic motion back into the experience. On the right-hand side of my poster, I've included 4 additional images that highlight a couple of other projects and interests of areas of mine. The top shows a robotic hand with a glove that has sensors on it, shaking a human hand. And this project is focused on understanding remote contact social interactions. So for example, doing handshakes remotely through telerobotic platforms. Another area of interest of mine is thinking about data in a multimodal way, particularly data that is highly visual or organized in spatial representation, such as bar charts, line graphs, diagrams, and maps. And so we think about data in terms of representing it through touch, by vibration, through sound, both sonification techniques and text-to-speech, and through the visual display. The third image is an intermodal system, the first instantiation of which we're calling the quad. This is a tool for thinking about and learning quadrilaterals and shape transformations within that class of geometries. And what's interesting about the quadrilateral is that there's both a virtual and a physical representation of it, and there's communication between the two. And so how do we think about expanding the capacity of educational content to include all of these dimensions of learning? And then the last project that I've highlighted is our work with the St. Louis Lighthouse for the Blind and the St. Louis Blues Blind Ice Hockey Club, where we're thinking about next generation adaptations to the puck to support the gameplay. Thank you so much for listening. I'm looking so forward to meeting each and every one of you in Boulder, and I'll see you soon.
Hello everyone, my name is Nicolas Prudencio. I am an international graduate student. I am doing my PhD in mechanical engineering here at St. Louis University. I work at the Chrome Lab, and I basically I'm working with haptics, education accessibility. I have to design, in some cases, some embedded circuits, and I really like doing additive manufacturing because we build basically everything here at the lab. We use 3D printers. We have to program some microcontrollers also to develop and to build the wearables we're using. So basically my project is focused on developing some haptic wearables to work with deaf and blind children. What we want to do with these wearables is to teach them the concept of numbers first, and then in the future we would like to teach them some arithmetic. I know it will be a little bit complicated, but I think we can do it. And so one of the first challenges we're going to face is to build the whole framework, how are we going to develop the stimuli in a logical and useful way in a way that the participant or the deaf and blind children can understand what we're trying to transmit. So in this case, we're going to use another wearable that we also built, and it is basically a heart rate monitor, and it will measure the beats of the heart, and it will work as a feedback device that will send the information of the heart rate frequency to the wearable that is going to produce the stimuli, and then that way we are going to have a logical relationship between the stimuli and the heart rate frequency of the participant, and that way we can accomplish the first step of the project, that is teaching children the concept of numbers. So as you can see in the right part of the poster, we have a picture of a mannequin with a bunch of wearables attached to the arms. So these are the prototypes we built. We have one haptic wearable with a motor vibrator that basically vibrates, and that's a way we transmit the haptic stimuli. The second wearable is using a servo motor. These two wearables work pretty easily to program and to build. But then we believe that it could be better if we have another wearable with a regular DC motor. In this case, the thing is a little bit more complicated because we have to design the whole control system to control the rotation angle of the regular DC motor. And as you know, a regular DC motor spins quite fast, and then we had to design the whole electronics to control the rotation angle and everything. And actually, the servo motor and the third prototype we developed have direct skin contact. And at some point, trying to build the sensors to know the exact rotation angle, we realized that we don't really actually need skin contact. We can transmit the haptic stimuli using just the vibrations of the poppings of the push button. So that's the way we got our fourth prototype. And now we have all the prototypes built. What comes next is what we are going to try to do now is try to redesign the whole PCBs, and we're going to shrink the size of all the prototypes because we are basically going to work with very young participants. And if we have a big wearable, it will be huge compared to the body size of the participant. So that's basically my project. We are trying to develop wearables to teach deaf and blind children the concept of numbers first, and then in the future we hopefully will be able to teach them some arithmetic. That's all. Thank you.
Hello, my name is Scott Lambert. I introduce myself as Scotty to most people, but either one is fine. Most people at work know me as Scott, so that's probably what you'll hear most. But truly, either one is okay. I live in St. Louis, Missouri. I am from the Pacific Northwest, but find myself at St. Louis University right now, so live in Missouri. I work in the CHROME lab, the Collaborative Haptics, Robotics, and Mechatronics lab at St. Louis University, which is also our website. The link is there, but I found it easiest just to Google CHROME lab Google site, and it's the third link for me when I Google that. So rather than say out the whole URL, that's how I find it. We work in like robotics and haptics space, but I'm more researching educational tech and the idea of accessibility engineering. Hybrid engineering is also kind of what we do, but also like 3D printing and electronics, which is involved in the project I'll talk about here in a sec. So the things I'm kind of interested in this week are the first question being, how can engineers, designers, educators, and others, really anyone, work together to imagine and create novel learning experiences, of which the quad is an example. And it demos sort of atypical or non-standard learning platforms. So I'm curious what other subjects or topics are primed for new methods of instruction through increased interaction. And the answer might be all of them, which is great. But I'm curious what people think of and what might be most well-suited for something like the quad, which is a tangible learning tool for geometry that seeks to provide interactive learning experiences to diverse learners. So it's a tactile tool that's 3D printed so that students can touch their learning and directly interact with what they're doing. Through that, we're also developing the ILS, the Intermodal Learning System, and the motorized quad, which is a part of that, which I also want to highlight. The ILS is a multimodal input-output learning framework that we'll probably hear more about this week, but seeks to provide basically a intermodal system that allows students to access information whichever way they prefer. So equitable learning system that's visual, auditory, and tactile, so students can get to the same info in whatever way suits them best. One of those modalities is the motor quad, or Franken quad, because it kind of feels like it's alive, because it moves to a desired location for you. In the picture on the top right is an example of the Smart Quad, one of the quad tools connected to the virtual sim. So that is a tactile input and a visual output. The simulation also has audio output, so that students can hear what they're creating and some of the properties as well as shape identifications. And that also feeds then back to the Franken quad to then recreate those shapes in a tactile way. So a student could tactilely create a parallelogram, hear the properties of a parallelogram to know that all the sides are parallel, and then another student could then experience that on the motorized quad. That parallelogram that the first student created is then recreated. That's the motorized quad. And then finally, the last picture is the base quad. So that is just the no sensors, no electronics going on there, purely a shape exploration learning tool that is meant to be touched and interacted with through touch. It's a tactile device that students can get their hands all over and learn with. And that's about it. I'll see you guys all in Boulder. I'm really looking forward to it.